Hello everyone, let's start the chapter 2 of the quantum mechanics by Zetili. So we will start with the linear vector space. So before we talk about linear vector space in detail, let's talk about the quantities which are encountered more often in physics. So these two quantities are scalars. One among them is a scalar, the first one, and these scalars are the quantities which only have a magnitude, that is their whole description can be given by just a number. For example, density, time, temperature, mass, etc. And then there are other type of quantities which are vectors, which not only have a magnitude but they have also a direction associated with them. For example, displacement, velocity, force, etc. So all these quantities have magnitude as well as direction. So now how do we represent the vectors? For example, if I have a certain vector like this, let's suppose this is a displacement vector with a magnitude p, and it is represented analytically like this, p with the arrow on the top of its head. So this arrow means that it is a vector. Now this is the general representation, and the graphically it is represented by a arrow with a tip, and this tip points towards the direction of that vector, and the magnitude of the vector is usually taken as the length or in proportion of the length of this vector. So this is a vector. Now we will generalize this concept for the study of quantum mechanics, and these generalized vectors are cannot be thought of as only having a magnitude and direction. Of course they are included in that vector space, but not only that, because there will be other types of quantities which are not having a magnitude and a direction like in a conventional way, but they still are vectors. So let's look at what is a linear vector space. Suppose you have a mathematical space which comprises of two sets of elements and two sets of operations on them. First is the set of vectors psi, phi, chi. So these are the set of vectors, and the scalars will be denoted by these alphabets A, B, C, which are in the lower case. So now let's look at the second one. There is a rule of vector addition and their multiplication by a scalar. So let's look at these operations one by one, what are allowed. So the rules are as follows. If there are two vectors which belong to same space, for example I have two vectors psi and phi which belong to some vector space V, then in order for this V to be a vector space, you should have psi plus phi is belong to this vector space V again. That means the addition of these two vectors must also belong to the same vector space. And there is not only this rule, there are other rules also. Then there is a commutativity of addition. The order of addition doesn't matter, psi plus phi or phi plus psi, both are equal. The associativity in of addition is like this. So psi and phi, if you add first and then add chi to them, or you add phi and chi first and then you add psi to them, it doesn't matter, the answer will be the same. And then comes the null vector. This is a additive null vector. That means there must exist a null vector 0 such that, or O, such that psi plus O is equal to psi, or O plus psi is equal to psi, because this follows commutativity of addition. So now the fifth one states that there must always be an inverse vector. That means for a vector psi, there must be an inverse vector minus psi inside that space. Then only you can call it a linear vector space. The sixth one is that if there is a vector psi, and if I multiply it by a scalar that is usually denoted by the lowercase alphabets A, B, C, like that, then this A into phi If psi belongs to a certain vector space V, that means A into psi will also belong to that same, must also belong to that same vector space. Or any linear combination of psi and phi, if the phi is also belonging to the same vector space, then any linear combination like A psi plus B phi should also belong to the same vector space, in order to be a linear vector space. Now the distributivity of addition, you can look here that A into psi plus phi must be equal to A psi plus A phi, and A plus B into psi must equal to A psi plus B psi. And then there is a associativity, that means associativity of multiplication, that means A into B psi is equal to A into B first, and then you multiply it with psi. It doesn't matter, both will be same. Now for each vector there is a unitary scalar, that means there is a identity I such that I into psi is equal to psi itself. You will get back the same result. And there is a null vector 0 O such that O into psi is equal to O. Now let's look at examples of the vector space. What can be the example? Let's look at a number line, a real number line. I will draw properly here. This is a real number line. It is going like this. And this is origin over here. And then we have positive real numbers like this. Let's say this is 1, this is 2, this is 3, and so on. And this is -1, -2, -3, and -4, and so on. So this is a number line. Now the question is it a linear vector space? So what are the checkpoints you have to check? The checkpoints are this. There must be the rule, there must be the case that psi plus phi, if psi and phi are the elements of that space, then their addition must also be the element of that same space. There is commutativity, associativity, and existence of null vector, and these 5, 6, 7, and 8 rule, and this one 9th. So let's look if it is there. So the first was that there sum must be in the same vector space. Let's take any two numbers. Let's say 1, and other number I will take is 4. So do they belong to this number line? Let's say this is R. Yes, 1 belongs to R and 4 also belongs to R. Then 4 plus 1 must belong to R. Is it actually I shouldn't write it directly. Is 4 plus 1, which is 5, is it in R? Yes, of course it is in R. So it is phi. So phi is part of this real number line. Yes. And then there is a commutativity and associativity of addition. So of course these numbers follow them. You can check by yourself. There is a existence of a null vector 0 such that 1 plus 0 is equal to 1, or -4 plus 0 is equal to -4. And for each element, I won't call these vectors, but I will call these as element. For each element 1, there is a inverse. That is, we have said that psi plus minus psi is equal to 0. If psi belongs to that vector space, minus psi also should be from that vector space. Otherwise it won't be a vector space. So to that space, okay. So now 1 plus -1 is 0. So for each number here, there is a same number with a negative sign. So there exists additive inverse. So now let's look at the distributivity of the with respect to the addition in terms of multiplication. For example, we have seen here that a into psi plus phi must be equal to a a psi plus b phi, etc. So all these are followed by these numbers, and you can cross check if you want with this. And there exists one, this identity 1, such that 1 into any number from this number line, let's say 8, it will give you back the same 8. So this is indeed a vector space, linear vector space. And let's look at another example. Let's say I have two-dimensional real number lines. So this is x and y. Let's say I have a point over here. This is point 1 and 1, and this point's location is given by this vector, this. So this whole space is there like this. This is the example I am giving you. Is the set of all such points which are given by x and y coordinates, is it a real is it a linear vector space? The answer to that is yes, it is a linear vector space. Why? Because I will tell you how. This is a vector. Let's say this is I cap plus j cap. Since x is in x direction we have I cap, and in y direction we have j cap, we wrote like this, I cap plus j cap. Now this I cap plus j cap belongs to this space only. Now we know that vectors follow the commutativity of addition, associativity of addition. There can be another vector like this, then your addition will be the, because of the triangle law of vector addition, I can say this is the resultant vector. And if you do it again like this, first you take this vector and then take this vector, it doesn't matter. So associativity is proved. There is a null vector because 0 is over here, and there is always inverse vector like this, which is -1 -1, so that if it is added you will get null value. And linear combination rule is also there. You can check yourself this one. And identity is also there. If you multiply it by a number, let's say if you multiply this vector by a number 1, then you will get the same vector again. So this is the existence of identity. Now on the other hand, suppose if I have yes, I will take this space. So suppose if I have this number line, this is origin, and in the positive, in the right direction, all the positive numbers are there, 1 2 3. So this number line is r, but for a positive, so let's denote it like this, positive real numbers. So now is it a linear vector space? Does it follow commutativity? Sorry, not commutativity, this property. If psi is belongs to V and phi belongs to V, it means psi plus phi must belong to V. If I take 4 and 1, 4 plus 1 is phi. So it follows, it seems like if I take phi here, phi plus 4 9, 9 will be there. So it follows that commutativity will also be followed. There is a null vector, so this is also followed, that is a null additive inverse, sorry, null addition is there, null additive vector. And then there is this case that if psi is there in a space and if minus psi is also there in that particular space, then it will be linear vector space. If it is not, then it won't be a vector space. So for 1 there must be a -1, which is not here. You cannot see any negative number line over here. So this is not a linear vector space. So you can think of several linear vector space and comment down about these.